folks, welcome back to the workshop. My name's Brent. In the last few shaper videos I did, I talked about the importance of having a well-tuned and accurate machine to giving you really good results with your spindle molder. I had a bunch of people reach out and ask me to do a video on this. So in this video, we're going to talk about some of the simplest techniques that you can use to make sure your spindle molder is running accurately and in a condition to give you really good results. Hope you find it helpful. So I just finished rebuilding the smallest of my Wadkin shapers. You've seen it on the channel a fair amount. I took it all apart, cleaned it, everything, did the bearings and the whole works, and I put it back together, and it runs really well, but it's time to make the final assessment that it's running accurately and is well tuned up before I put it back into service. I have a lot of work coming up for all my shapers as I outfit my new shop and do all the interior and exterior millwork and flooring and the whole works. So the time is now to make sure that it's accurate and it's going to give me excellent results. Now what's great about these very, very simple machines is that they're super easy to maintain and they're super tough and they're super rugged. However, they're all very simple machines. So if you've got a more sophisticated spindle molder that has maybe a sliding table or a tilting arbor or something like that, you may have to use a couple of additional techniques, but all the ones that we're going to go over here today are still going to be a great place to start. Similarly, all the assessments that we're going to do today are all going to be using very simple tools that most woodworkers would have around the shop anyway, but I am going to show you a couple of additional techniques that are made easier with some more sophisticated tools. Let's take a look. Okay, even with just this basic set of tools, you can go a long ways towards assessing or troubleshooting your shaper. Fortunately, many of these tools are the type of tools that a lot of woodworkers would have anyway, especially those that use machines a lot. You've got a good reliable straight edge, you got a set of vernier calipers, you got a set of feeler gauges, you have a dial indicator, this one happens to be digital, and a good reliable square. A fixed engineer's or machinist style square would be better than this one, but mine are 1,000 miles away at my new shop, and this is a good stair that's been treated well and will do just fine for today. Now, a few things that you might not have, but would make a few things a bit easier to be accurate with, would be an outside micrometer, such as that, a test indicator, or if you think you need to assess the bore of your tooling or the socket in your shaper, if you have one, a set of inside micrometers or telescoping gauges might help there as well. And also, if you want to get a little even more fancy and start to evaluate your spindle outside of the machine, a set of V-blocks would be helpful too. I like to start with the fence off, and then we'll take a look at that separately later on. The first thing that I do is take the spindle and the rings out and clean the table all off. You want to get off any burrs or sapwood or sawdust buildup or anything like that. You can use brake clean or lacquer thinner, but make sure when you've done this that you retreat the top or it'll flash rust on you. I like to start with assessing the flatness of the top first. Not only because the flatness of the table is important itself, but also because it'll help you interpret results from the subsequent testing down the line. For example, if you have one little low spot somewhere, it may well show up in the subsequent testing and may mislead you into thinking that you've got an issue you don't have or a bigger issue than you really do. You can do this with a simple straight edge and a feeler gauge. You can write it right on the table, clean it off later, or you can make a little grid on a piece of paper like I did and assess, say, every 2 or 3 inches or so, remembering to occasionally do the odd test on an angle as well. So when you get your results, set that aside for now. Install the rings and make sure that they don't rock and are also flush to the top. You can use a shorter straight edge for that. So if you find your shaper table is really out of whack, there's not a heck of a lot that you can do about it in the home shop. Yes, you could send it off to be Blanchard ground. That would be quite expensive, but it would also affect how the table rings fit. It would affect the geometry of your miter slots, but it also could affect your fence depending on how it's attached to the table. So it would have to be quite a bit out of whack in order to justify that. Now, I found a real low spot on my table, and at the end of the video, I'll talk about why I decided not to bother dealing with it at all. Many of the next steps require you to reinstall the spindle back in the machine. Make sure the spindle itself is clean as well as where it sits into the quill, checking carefully for damage such as burrs or dents. Reinstall the spindle carefully, set the height where you normally use the machine, and lock the height. Looking at the spindle itself, there are a few things we can do even with our basic tools. Using a test indicator, we can make an assessment of the runout in the machine, again making sure that the spindle is installed in the machine properly. Checking a few different places in the spindle, focusing on where the tooling will sit, and you're looking for less than around 3 thou. So if you have excessive runout, there's not really much a non-machinist can do about it, but if you take it to a machine shop, they can give you a sense of the total indicated runout, the straightness and the cylindrosity of your spindle, which helps you isolate the problem to either the spindle itself or just how it sits in your machine. The other thing you can do easily is check the diameter of the spindle, with an outside micrometer being better than a set of vernier calipers. Sometimes the spindle on older machines are made to different tolerances or are worn from heavy use. This can result in more clearance between the shaft and tooling than is necessary, which in turn can affect performance and balance. In this exaggerated example, you can see the effect of this. Some clearance is required to make the tool changes easy, but excessive can be a problem. You're looking for less than a thou under the nominal size. If you're using older or worn tooling and have a problem, it may be worth checking that too. So if you decide you need to have a new spindle made for your machine, it's not a difficult task for most machine shops. It's early 2025 right now, and I could probably have a spindle made for either of my machines for in the range of $350. Typically what I do is I'll bring the spindle into the machine shop and they'll measure the bottom where it fits into the machine and copy that, presuming the bottom is still in good condition. They'll copy that and use it for the new spindle. However, if your spindle is very worn, or perhaps it's an old spindle that is made to different tolerances, they may be looking to you for a bit of guidance on how to machine the top. Machining the top is not difficult, but they need to know what size to make it, what diameter to make it, because spindle molder spindles are typically not made right on the money. In other words, a 30mm spindle is usually slightly smaller than 30 millimeters. Now, it's a whole subject you can get into, and we won't get into the details here, but typically spindle molder tooling and spindles are made to what's referred to as an H7 G6 tolerance. The H7 refers to the diameter, the acceptable diameters for the bore of the tooling, and the G6 refers to the acceptable diameter range for the spindle itself. You don't have to understand all that because your machinist probably will. Essentially what it does is if you follow those standards, the tooling will always go on and off the shaft fairly easily. When I have my spindles made, I usually make them on the larger side of that, so it might be an H6 or an H7 clearance, which makes it a little bit tighter, but the spindle will still always go on and off. But there's very little kind of leeway or tolerance for any burrs or dents on the spindle, but I've never had a problem with it. The other thing to consider when having it machined is the very base of the spindle, where the tooling sits, has to be machined in a way that allows your tooling to sit all the way down, because at the root here there's a small radius, and when the machine shop makes your spindle there will also be a radius here, but you want to make sure that they're compatible in such a way that the tooling can sit all the way down, because it's typically referenced off of this small shelf down here. The next easy test is to check the spindle with a good square. A good certified machinist square would be better than my combination square, but this will serve to demonstrate the process. With the light behind the square, you should be able to see any gap fairly easily, and you can measure it with your feeler gauges, looking for 1/2 thou or less on a 4 or 5 inch spindle. If you have a gap at the top or the bottom of the spindle and it reverses when you move the square to the opposite side, but don't rotate the spindle, you may have a spindle that's out of square to the table on that axis. If the location of the gap stays the same, when you rotate the spindle along with your square to the opposite side, you may have a bent spindle. Measure in a few different places around the circle, but consult your flatness data too to make sure that your measurements aren't being thrown off by a little low spot on your table. What many consider to be a more accurate way to check spindle square is to clamp your straight edge between two good accurate collars and measure the gap on opposite sides of the table. Again, doing this in multiple locations around the 360-degree swing of the spindle. Use your flatness map again to help interpret your results. However, if your spindle is bent, you'll find any observed discrepancy is not necessarily repeated when you rotate the spindle 180 degrees. Here you see I've inserted a shim underneath my straight edge to simulate an exaggerated version of what a bent spindle would look like, and as I rotate the straight edge, the discrepancy follows the straight edge instead of staying at the same spot on the table. So before you decide your spindle assembly is not square to the table, repeat your measurements with the spindle rotated 180 degrees. So repeat this process at different points around the circle, but also while clamped at different positions around the spindle. A straight spindle that is simply out of square to the table will always give you the same results, where a bent spindle will result in different readings depending on where you clamp the straight edge relative to the plane of the bend. One other important assessment is to verify that the axis of rotation of the spindle assembly, or the quill, is square to the table. This is referred to as tramming the quill, and verifying that your quill is in tram to the table is best done with a dial or a test indicator, and you can attach that to the end of your straight edge, or you can use a stand as I'm doing here right on top of the quill assembly, or if your spindle is not removable but is in good shape, you can attach the mag base to the side of the spindle. Remember that table flatness issues may be confused with out of tram, so you're looking for the general trends here, not so much worried about little bumps and dips. I wrote the results right on the table so I could easily evaluate my progress as I fix the issues. So what do you do if you find out that your spindle is out of tram to your table? Well, as with a lot of these issues, the resolution is really going to be machine specific. But I have two different spindle molders that represent kind of the two general or two main ways that they put together machines. This small machine, the entire quill assembly and motor and the whole works is actually hanging from the bottom of the table. And typically what that results in is the four mounting points that attach it are actually fairly close together. So for this machine, when I adjusted the tram on this, I only needed to use 1/1000th of an inch shims, and I actually ended up making quite a bit of difference because the four mounting points are so close together. On my larger machine, which is typical of a lot of large machines, all the quill assembly and everything is actually attached to the big cast iron base, and the table is actually kind of floating on four secure anchor points. So it makes it really, really easy to dial in as best a tram as you can possibly get because the four mounting points are so far apart. Now, as for the shims itself and the approach to shimming, you can buy what are called machine shims. They're stainless steel and they're very hard and they won't oxidize. And they are the best for it. I've always used brass shim stock and made my own. Technically brass is a little bit compressible, but I've never had a problem and I've never had to go back and do it over again. The trick is to sneak up on it, and it's a bit of a painstaking test for your patience. What you've got to do is make a small adjustment at a time. I recommend adjusting two adjacent points together. For example, if your machine is out of whack this way as well as that way, don't try and just shim one side. Do two and then do two again and sneak up on it. And have patience. Make your shims or make your adjustments. Tighten it all down. Use a torque wrench so everything is consistent, and then reevaluate. If you need to do it again and make small steps, and eventually you'll get there. Looking at the fence, you want the fence to be 90 degrees to the table at all positions, and the fence plates coplanar to each other at all positions along its range of adjustment. A good straight edge will help you verify this much in the same way as you would do with jointer tables. So if you found a few imperfections with your factory fence that you want to deal with, resolving the issue is probably going to be like some of the other things that we talked about, where it could very well be machine specific. So if you're lucky, your machine has some built-in features that let you accommodate for that, and you can deal with the imperfections with sort of onboard systems from the manufacturer. Otherwise, you might be looking at shimming in behind some of the fence plates to deal with issues, or probably a more expensive but permanent fix would be taking it to a machine shop and having some of the issues dealt with there. Now, there are many reasons to use an auxiliary or false fence on the spindle molder, but one of them can be to deal with some mild imperfections with your factory fence. If it's made of stiff and rigid material, it has the effect of sort of spanning and bridging some of the imperfections, leaving you with a nice straight fence. Also, if it's made of solid wood, you may be able to machine it to accommodate for or compensate for all the fence imperfections. This is more straightforward. With a straight fence scenario, it's a little more difficult if you're using an offset fence or a jointing fence, but it can be done that way as well. You can simply cut out a space for the tooling, or you can make a breakthrough fence like I did here for some cabinet door tooling. I've spoken about breakthrough fences a few times in the past, but I'll put a link in the description below to a video that describes a great and safe technique for doing this. If you're not interested in repairing or accommodating for your factory fences imperfections, you can actually buy aftermarket fences that contain a number of really, really interesting features. They're quite expensive, but they do have a number of great safety features and a number of features that make your work a lot easier to do. I'll put a link to them in the description down below. Okay, a couple quick tips from somebody who's done this a few times. Remember, this is woodworking, it's not rocket surgery. Resist the temptation to chase that last 0.5 of an inch. You'll probably never get there, but you'll definitely drive yourself crazy. We're dealing with wood, and the wood's going to react just to the act of being machined, so chasing utter perfection is probably not a good use of your time. Also, pick your battles. Remember I mentioned I had a low spot on this machine? It's way back here behind the fence. There was no way I was going to be able to get the entire table dialed in, but I realized that 99.9% of all the work that I do is in the front of the table, which I could get dialed in really accurately. So I just didn't bother trying to get the whole table trammed in. I know that low spot is there. If I do any huge circular work where I may be using this part of the table, I'll keep it in mind, but the odds are good it'll never actually bother me. It's a bit of a dry video, but I know a number of people were asking for it, so I hope people find it helpful. I want to thank my machinist friend Mark for a bunch of pointers on this. Thank you for watching, and we'll see you next time.